in his book, right, in his book of 1917, Einstein talked about the principle of equivalence, okay? And it's important to know, again, that, the reason his theory was accepted, general relativity as a gravitational theory, over Newton's was because of the speed of light. Newton's equation said that gravity acts instantaneously. And Einstein said, no, you have this, both sides of his equation. On one side, you take the mass of the object, it weighs down space-time, this field, this thingy, right, weighs it down, and because it distorts space-time now tells the object how to move. If you're walking on a trampoline, right, and you press down, well, you pushed the canvas downwards. That's what the object does. The mass, as they say, pushes it down. But now, because the canvas has been distorted, your trip is also distorted. Now you sink and your movement is affected. And that's what general relativity says in a nutshell. Objects distort the space-time, and space-time, because it's distorted, affects the movement of the object. That's it. That's in a nutshell what Einstein discovered, invented, or whatever you developed. And part of that was this principle of equivalence. He started thinking about this, and this is what he writes in his book about it, about the principle of equivalence, how he justifies it. I'm going to go a little slowly here because not everybody can understand what Einstein did with his equation, even though it's a relatively simple equation. If you had high school, you should be able to follow through, but I'll go slowly. Okay, so here it goes. He says, according to Newton's law of motion, we have, and I put the ones in red there, those are my numbers, okay, but the rest is all his. Force equal inertial mass times acceleration, okay? If now gravitation is the cause of the acceleration, he's saying gravitation is the cause, right? No, gravitation is a concept. You can't say that's the cause, but that's the language that he used. We then have force equal gravitational mass times intensity of the gravitational field. And there you see the equation on the side, okay? Force equals the gravitational mass times acceleration, okay? From these two relations follows, and he puts acceleration on one side of the equal sign and puts everything else on the other. He puts gravitational mass over inertial mass. He's going to turn that into 1. He's going to say that gravitational mass is equal to inertial mass, which is what the principle of equivalence is all about. And he's going to multiply that whole factor by intensity of the gravitational field. Okay, that's number 3 there. And number 4, he just, essentially he says, gravitational mass is equal to inertial mass, acceleration being the same in both cases. So now he explains, he says, if now, as we find from experience, the acceleration is to be independent of the nature and the condition of the body and always the same for a given gravitational field, then the ratio of the gravitational to the inertial mass must likewise be the same for all bodies. By suitable choice of units, we can thus make this ratio equal to unity. He's going to say that gravitational mass, number 3 there, gravitational mass over inertial mass is equal to 1. He's going to equate those two, the G mass and the I mass, right? He's going to equate them. He's going to put that as a 1, and therefore acceleration is going to be equal to what's left, which is the intensity of the gravitational field, okay? And so he said the gravitational mass of a body is equal to its inertial mass. It is true that this important law had hitherto been recorded in mechanics, but it had not been interpreted. In other words, he's saying other people came up with this. He's saying he's going to give you the physical interpretation of why gravitational mass and inertial mass are equal. In other words, if you put one over the other, you get a 1. Okay, that's how this principle of equivalence was justified, and ever since, the mathematicians have been using it. Okay, so what does this mean in physical terms? Well, Einstein gave an example. He said, look, imagine you're in an elevator, right? You out in space, right? Well, you would not know if you have the simple gravity of the Earth, right? Like if the elevator is just sitting on the earth and you drop a ball, it would fall at 9.8 meters per second square. Or if you're in a rocket that's accelerating at 9.8 meters per second square, in other words, 9.8 meters per second. In other words, you're going faster and faster and faster. And you can see the equations. On the left-hand side, you have force equals mass times acceleration. And on the right-hand side, you have Newton's equation there. If you take the one on the left and the one on the right, they both have the same value. So he's saying that you really can't tell the difference if you're in an elevator, whether you're accelerating away from the earth or you're falling towards the earth. He says he had a thought experiment. He said, well, what if I'm accelerating with my elevator in a rocket? What if I'm falling with my elevator, because the rope was cut off or whatever? And so he looked at those, one going up, the other one going down. He says, hey, they're equivalent. Intuitively, they seem to be equivalent. And from that, he came up with his principle of equivalence, saying that he's the guy who justified it, that explained it, okay, to the mathematicians. And what's interesting, because of that, he arrives at this conclusion, okay? He's saying that if you're accelerated upwards, what happens to a flashlight that you have in your elevator, the light is going to curve. That's what he says, okay? Especially if you go at the speed of light, you accelerate at the speed of light, gravity is going to bend light, okay? And a lot of people didn't accept that until 2 years later. He says this in 1917. 1919 was a great year for Einstein. He got divorced. He got married again. And he promised his ex-wife, Mileva, that he would give her the money that he won, if he won, for his Nobel Prize, which came 2 years later in 1921. But he was already being proposed for a Nobel Prize, not for relativity. He never got a prize for relativity. He got it for the photoelectric effect, something totally different. But 1919 was a great year for him, not only because he got divorced and married, but because Arthur Eddington confirmed his theory. Okay, in other words, here we have good old Arthur Eddington, and there was this news coming up in those days, several papers. This is just one example, and where Arthur Eddington essentially, through an experiment that they did in the Pacific Ocean and several other places, they were able to measure, they were able to photograph a star behind the sun during an eclipse of the sun. Okay, so the moon came up there, blocked the sun. They could still see the light of a faraway distant star, right? Going around the sun and reaching our eyes, reaching the camera, right? Because of that, they said, oh, Einstein's confirmed. Einstein became an overnight sensation. Okay, as you can see, these people made a big fuss about it. Okay, says one of the most important discoveries of the century. Okay, light curves around the sun. And so, yeah, they since that, they proved it many times, they say, okay? And no, light does not curve. Light always goes straight. And if people knew a little bit about physics, right, they would know that there's this ray reversibility. The principle is called the principle of ray reversibility. Light always retraces its exact path, okay? And yeah, with the rope model, you can see why, because light has no way of getting lost, right? It just torques in situ, right? And so light goes in both directions. So it doesn't matter how much you move an atom. That's at the end of this, right? It doesn't matter where you move them. Light will never get lost because light always travels along the rope. Okay, it's a torsion. It doesn't even travel really. It's just a torsion, and you get the bumps at the end. Anyways, the point is that you can do what Arthur confirmed, right? Eddington confirmed. You can do it with straight lines. You see these patterns where you can do a curve with a bunch of straight lines, right? And that's essentially what is happening in real life. Okay, at least that's our position here. So what happened? They confirmed Einstein. Einstein became a sensation, right? And because of that, today we have all these people who measure what Einstein predicted, which is that the principle of equivalence, that inertial mass is equal to gravitational mass and vice versa. And so what they do today is measure, and they say, let's see how close we can get it. You got all these tests, all these measurements that they've taken. This is out of the Wikipedia, by the way. And all the tests that they have done year after year after year, right? Where they go to ever finer, more decimal points. I measure the table and I say, look, the table measures 1 meter, right? And the other guy comes over and he says, no, Bill, you're wrong. I measured it with a better caliber and I found out that it's 1 meter, 1 micrometer, 1.1, 1.0001, right? So he measures it more accurately. And what they're doing is measuring it to more decimal points. And I would suggest to all these people, they stop measuring it. Why are they measuring? This is it's a conceptual issue, subtly conceptual. All you have to do is understand why, and then you don't need to measure ever again. And here you have some of the experiments that they're going to be doing in the future. Experiments are still being performed at the University of Washington. Future satellite experiments will test the weak equivalence principle in space to much higher accuracy. And they have all these tests, all these proposals, right, of how to measure, inertial and gravitational mass ever more precisely. And I'm saying, why are these people measuring? Don't they have anything better to do? I mean, what's the point of all this measuring? And people might say, well, Bill, you don't agree with the principle of equivalence. You say it's wrong, it's inaccurate, it's not perfectly equivalent. What are you saying? No, let's make it absolutely clear. The principle of equivalence is perfect. There is perfect equivalence. You don't need to go to more decimal points, please. It's principle of equivalence says that inertial mass is equal to gravitational mass. It had better be. It had better be, okay? We're talking about the same thing. So inertial mass and gravitational mass is the same thing, okay? So we don't need to measure anymore. Take it from me, they're equal. They're exactly equal. They can't be anything else. And so for this, you need to understand why. And once you know why, we're done with physics. We don't need to keep measuring and getting more equations. Totally irrelevant. We can do this simply by understanding why it's the case. Okay, so that's what we're going to look at now. And there's a couple things that we got to challenge about the principle of equivalence. Let's go with the first one, and so that we get the rules straight. First one is that there are no principles in science. Okay, principles are stuff invented by the mathematicians. They invented axioms. All kinds of words that they use there, axioms, principles, what other one? Well, another one doesn't come to mind right now. But the issue is there are no principles. Oh, the other one would be principle, right? There are no such things as principles in science, in physics. That's stuff that belongs exclusively to mathematicians, okay, not to science and physics. Principle may relate to fundamental truth or proposition. We have no truths in science. There are no truths. Okay? Truth means I shoved my theory down your throat. That's what truth means. That's what proof means. That's what evidence is all about. That's why they do experiments, to collect evidence so they can shove it down your throat. So in science, we don't do that. In science, we explain, you understand, we're done with science. What continues is known as religion. You can believe in whatever theory you want after that in the comfort of your own home, okay? And so you have those definitions there, the other one from the dictionary.com. A fundamental, primary, or general what? Law. No, we have no laws, okay? That was another word that I missed. Laws, truth, none of that belongs to science. We don't have laws in science, okay? That we follow or that we disobey, any of them. We don't deal with laws, okay? Laws, they're referring to mathematical equations. They say, oh, the law, diameter is equal to circumference, or you can say circumference divided by diameter gives you 314 pi. That's a law, you can say. Great. Or maybe it's a principle because I think they haven't found the last decimal point. So meanwhile, it's a principle. No, it's all nonsense. Absolute nonsense. We don't have laws in physics. In physics, you explain, the other guy understands, we're done with physics. Okay, so we need to know how these words enter physics and why they should be banned. They have no place in physics. Okay, what we need to do is, another thing is understand what it is that we're trying to get. What is this equation? Force equals mass times acceleration. What are we analyzing? What's in front of us? Okay, and so here we start there. We have force equals mass times acceleration. That mass there, what is that? Well, that's an object. That's what it is. In this case, I'm going to put an asteroid, okay? So we have a little asteroid, or big asteroid, I guess. That's an object. That's a noun, okay? That's a thing, okay? That's what the mass represents, okay? So we got that so far. Let me remove this. So we got the object, okay? Now, what's that thing called acceleration, okay? And acceleration goes like this. It's what the mass does, what the object does, okay? In this case, the asteroid is flying towards the moon, okay? We can watch it move, okay? It's all there in front, so we have both words kind of accounted for. We have the mass, the object. We have what it's doing, which is the verb there, the motion of the asteroid. So the first one we can see and say, okay, that's an object. That's a thing. It's got shape. No problem there. The other one, you have to watch the movie. You have to watch the movie of how the asteroid, goes towards the moon. Okay, so far so good. What's the issue? The issue is the other word. This is the word that we have problems with, the word force. Now here we have a real problem because force we can't see or touch, and we don't see it there. All we see is we see the asteroid, we see the motion, the acceleration, or how it approaches the moon, the speed or the motion, etc., right? But we don't see any mediator, and we don't see what's causing this whole thing. And that's what the word force represents, okay? The word force is the big problem here, and we need to account for that in order to understand, what's going on here, in order, especially to understand the principle of equivalence, right? Okay, so let's move on here. We're going to look at this word force, and here we have the principle of equivalence. I just want to make sure that we understand inertial mass is exactly equal to gravitational mass. So I'm not disputing the principle of equivalence. I'm disputing Einstein's explanation, his justification for this equivalence, and also criticizing the mathematicians of the last 400 years because they simply had something wrong. And that's what I'm going to go over right now. Here we have the gravitational force, okay? And you can see that this is what they do. They put force equals mass times acceleration, and they make it equal to force equals to the Newton's gravitational equation, which is force equals gravitational equation, mass times mass divided by distance squared. And that's a no-no. That's wrong. Okay, that's simply wrong. So they've been doing this for 400 years. They've been doing it 400 years. They've been doing it wrong. Okay, and so we start with there. You see, force equals gravitational, the constant g, mass over distance squared. What's wrong with that? Well, what's wrong with that is this. Okay, we have to remove the word force. It's not a force. Okay, it's weight, and weight is not a force. You don't have to move in order to have weight. You have weight anywhere around the earth at a location. In fact, that's what the word field means. The word field means that you have gravitational field. We'll just use that and forget about the magnetic field or electric field. If you have a gravitational field, what is a gravitational field? It says that at each point in space you have a different value. Each point meaning every location. You move a picometer and you already have a different weight. That's how fast gravity is. It's faster than light. It's like instantaneous. I hate the word instantaneous because instantaneous, again, we have a problem with that because instantaneous requires two frames of the universal movie. Even if you chop motion or time as many times as you want, you'll never arrive at one frame of the universal movie. You will always have two frames. Why? Because motion is defined as two locations, and so is time. Time requires two locations. So you need two frames of the universal movie. No matter how much you chop motion and time, you'll always end up with two frames of the universal movie by definition of the words motion and time. Okay, period. And so the issue here is that, that equation is the equation of weight. Okay, it's the equation of weight. And weight is a static concept, and it's a tension, because that means I can take a snapshot of you at some point around the earth at a given location. You already have weight there. It's a snapshot. You didn't have 2 frames of the universal movie or more. In a single frame, you have location, you already have weight. There's a weight with you for you with respect to the earth. Okay? So you already have weight. I can, if I could freeze the entire universe, weigh you there and give you a value, I could give you a value, say, here, you at this location, this is how much you weigh. If you're farther out or if closer, all bets are off. But at this location, this is how much you weigh. And as soon as you change location, well, you change your weight. So weight is location specific. And that's what Newton's equation says, because it's got distance in the denominator. And we're going to look at that distance because that's kind of suspect, that little distance there. But we're getting ahead of ourselves. So tension, it's a tension. Tension is not a force. Okay, that's what you need to understand there. Tension is not a force. Tension is a static concept. Force is a dynamic concept. No mathematician ever discovered that, because they talk about the tension on a string, saying, oh, you have to pull on a string. Not in tension. Tension, in tension. Not with tension. Tension means that no one wins the tug of war at that moment in time. Okay, so you can represent tension in a single frame of the universal movie. The way we do it, we put a dumbbell, two atoms bound by a stick. Stick made out of a single piece. It doesn't stretch. It doesn't shrink. That's tension. Tension is a stick made of a single piece. That's what tension is. It's not pull or push. Okay, and that's where these people, because they never paid attention to qualitative concepts or introduced them into their analysis, they ended up with quantitative analysis, and from there they ended up with tension being, a value, a number, and therefore it's governed by push and pull. That's how they ended up with that. Okay, so what's the issue? The issue is we're going to replace that force, right? We're going to replace it with tension. And of course, when you do that, then you reach the conclusion that this is not true. Okay, that force equals mass times acceleration is not equal to tension equal to Newton's equation there. Okay, so that's why they're not equal. Okay, in other words, you're talking about 2 different things. Does this mean that the principle of equivalence is wrong? No. In fact, this confirms that you don't need to measure anymore. They are perfectly equivalent. Okay, and that's what we're going to show now. Okay, here we have an asteroid, and it's falling towards the Earth, the one on the bottom. The one on the top is not, because it's a static. The difference is that little d, the little d like David, distance. The distance on the top is separation, whereas the distance on the bottom is distance traveled. And these people have confused a dynamic concepts such as distance traveled and confused it for, a static distance. These 2 equations talk about 2 different things. The one on the top talks about tension. Distance is distance of physics, meaning separation. And the one on the bottom, that includes distance traveled. Okay, that's what the difference is. And here we can see it, okay? The difference between this is a summary. Let me show this. What you got here is weight versus acceleration. The acceleration is the one from Newton's second law, force equals mass times acceleration. The weight is the one on the left, which is really a tension. And what is the difference? Well, in the first one, you can see the distance is static. In the second one, distance is dynamic. Distance is traveled, okay? It's a number. Distance is between 2 objects. The distance here is the one traveled by the object. That's, in other words, the object has a starting point. From there, it moves forward. Okay, and because it's moving forward in its forward direction, it's moving, and it's a distance traveled from that point, from its the starting point. That's different than the other one, which is a separation between 2 objects. Okay, Each frame in the movie depicts a static distance. You know, all you have is just two objects there separated by space. The second one, each frame in the movie is a cross-section of the itinerary of one object. In other words, if you put all these frames together, you get motion. But in a single frame, all you have is that. You have just the distance is decreasing in the direction of where it's going and increasing behind it. Okay, so what you have is that separate. In other words, it shows a distance traveled. Okay, and then here you have distance decreases, d1, d2, d3, when acceleration increases. Okay, and the other one's in reverse. Distance increases when acceleration increases. One case it increases and the other one decreases. Okay, the other one, the next one there, distance is towards the other object, distance is away from an unspecified object. And that's, again, when they move. But again, we're talking about static distances in the case on the left. But if you put several of these frames, then, 4, 5, and 6, and 7 apply. Distance is a measure of weight, whereas the other one, this is a measure of velocity. Okay, and then force increases when distance decreases. Force increases when distance increases. Okay, so you can see that these distances are not the same, but they treat them as the same, and they always put acceleration equal to whatever's on the other side of Newton's gravitational equation. That's not right. You can't do that because you're not talking about the same distances in these two cases. Okay, they're two different distances. The one on the left, the one for weight, is the distance of physics. It's separation. We don't care what the number is. Mother Nature doesn't know math, right? Never did math. And so what can I say? She never went to school, never learned how to do numbers. All she does is have objects and atoms. That's what she works with every day. And you have to be able to explain physics with just that. No numbers. We don't need numbers in physics. All we need to do is explain what's happening out there in the universe. Why, what causes a pencil to fall to the floor, for example. That's a physical phenomenon. And I don't need any numbers to explain what caused that to happen. And that's what Mother Nature understands. Mother Nature and Father Universe, all they do is move atoms from one place to another. They know nothing about math, about how fast or how much. They don't care about that. They don't deal with that stuff. That's us, humans, right? That's why these people have the numbers, but they don't have the explanations. Okay, so we got to find out what this distance is. And when you look up, you get scared because you find out that they never defined the word distance. Okay, they don't know what distance is. And you can see why. It says the distance between 2 points in physical space is what? The length. Now, length is not distance, and distance is not length. Why did they put the word length in there? And you can see there, length is a measure of distance. So when you look up the word length, it says it's a distance. When you look up distance, it says it's a length. Why? Well, because they're not talking about either length or distance. They're talking about distance traveled, about unrolling the tip of the measuring tape. So they say, how many meters? That's what a mathematician wants to know, and that's distance to him, right? But that's not this. Distance is just separation. I don't need any numbers to have the notion of distance. But if you want to measure the distance and unroll your measuring tape that you have already created a standard, the meter or the centimeter or the, the yard or the foot, you unroll the measuring tape, it's so many feet or so many meters. Okay, what did you do? You're unrolling something. You have a dynamic concept. What you have is the unrolling of the tip of the measuring tape. You're putting tiles on the floor. You create a tile, say this is the meter, and now you're putting tiles on the floor and counting all the tiles. That's different than saying there's a separation between two mountains, for example. Okay, and so the problem is that they define distance in terms of length in terms of distance. Why? Because to them it doesn't matter. If you're going to measure distance, like between the Earth and the Moon, you unroll the measuring tape or whatever thing that you use to measure that, and you just count and you say this is the number. This is how many kilometers. And if you're going to do length, length of the table, the same thing. You unroll your measuring tape. So whether you do one thing or the other, you're always unrolling a measuring tape. But that's distance traveled of the tip of your measuring tape or counting tiles or however you want to visualize that. That's not separation, physical separation, qualitative separation. Okay, and that's where the problem is. These people had no idea of these qualitative notions, and that's why they confused the two distances. And so here we have the rope model, right? You have an asteroid, and it's at a distance from the moon in this case, and there's so many ropes. Every atom of both objects are connected to all the others, but we're only going to use one atom from the asteroid, and well, you can imagine all the ropes connected to every atom that constitutes the moon. Okay, but here we put only one atom. Okay, what's going to happen? Well, we're going to have this situation where the one on the bottom, right, is going to be approaching the moon. Okay, and so we can see what's happening here with the ropes. Okay, as it approaches, the ropes fan out, and this is the acceleration of gravity. But you would have to watch a movie in order to understand it. You have to record each one of the locations of the asteroid in order to conceptualize this. Okay, so this is what we're suggesting. We're saying that every atom of the asteroid is bound, physically bound to every atom of the moon and vice versa. And as they approach, what you have is the ropes fanning out, and that explains the acceleration of gravity. Okay, so now we have a mechanism for the acceleration. What happens to the ropes? Well, let's look at it one frame at a time. Okay, here's the first one. Okay, you can see it gets closer. What happens to the ropes? They fan out. As it gets closer, what's happening next? Well, again, you can see they fan out, and they keep fanning out the closer they get. That's what's happening. Okay, so you can see how in other words, the asteroid really is not being pulled by the moon. What's happening is the ropes are fanning out as the asteroid gets closer and closer to the moon. So the asteroid is just drifting towards the moon, and the ropes fan out as it gets closer. And that's why it's a distance-related phenomenon. You know, the farther it is, the more distance, right? The denominator of Newton's denominator, the distance there is bigger. And being it bigger, the force is lower. And vice versa. When the distance is less, you know, the force increases. That's what's happening. That's just as simple as that. And so here we have different versions of this. You see when it's very far away, like on the bottom there, you have maybe it's 1 kilogram when it's at a great distance. Why? Because all the ropes come together, right? And as the asteroid approaches the moon, you can see what's happening. It goes from 25 tons, 200 tons, 500 tons, 1,000 tons, the closer it gets. Why? Because the ropes are fanning out. And what we're saying here is that weight, right? Using Newton's equation, weight is a function of how many ropes act independently. Okay? That's what it's all about. How many ropes at a given location. And of course, if you take all those locations, put it in a movie, then you're going to get the acceleration of gravity. Okay? So that's what we're saying. And so, yeah, that's the illustration of gravity. You can see we can illustrate gravity in a single, or weight in a single frame, because all you need to know is how many ropes are converging upon that point. Okay? And here you have it. Okay, you have Einstein versus my version. In his version, he says, well, I don't know why, but every time we measure, we find out that whether the rocket goes upwards, you know, the acceleration, 9.8 meters per second squared acceleration, it's very similar. You wouldn't be able to tell the difference if you're falling to Earth at the, you know, with gravitational acceleration, or if you were going at 9.8 meters per second square away from the Earth. In this case, you have force equals mass times acceleration on the left, and you have Newton's gravitational equation on the right. But see, with the rope model, you can finally visualize why it's the case. Because if you take a single atom, right, a single atom at a given location, right, it doesn't matter if you're going outwards or coming towards the Earth. At that location, they both have to match. And we're talking about a single atom here, okay? And so here, let me illustrate that so that you can get an idea, better idea what I'm talking about. Here it is, okay? we have a single hydrogen atom, just one hydrogen atom, okay? Weight is the number of ropes, effective ropes, ropes that have separated from, the axis, the main axis. If they separate, you have, they're not on the same axis, suddenly you have more effective ropes. That's what we're saying there. The closer you get, more effective ropes. The farther you get, the fewer ropes that you have. That's what it's all about. And weight is simply how many ropes at a given location. Here you have an atom, a hydrogen atom. It doesn't matter what it belongs to. It could belong to anything. It's at a given distance, right? You have all the ropes from every atom on Earth converging upon that atom. Okay? And so it doesn't matter if the atom belongs to a feather or to an elephant. It doesn't really matter, because as long as it's a hydrogen atom, in this case we're talking about hydrogen atom, it's got a single rope connecting to every atom, hydrogen atom constituting the Earth. Okay, it's more complicated when you talk about other atoms like carbon or iron or whatever. But the point here is the following. With that atom there, you don't know if it's leaving or coming, because at that point, force equals mass times acceleration is equal to tension equal to G mass 1, mass 2 over distance squared. At that location, they both have to be equal because it's the same number of ropes converging upon that atom at that location. That's why the principle of equivalence is correct in that sense. Okay, it is at that point the same value. Okay, so yeah, if you were to calculate with just one value, force equals mass times acceleration is equal to tension and what's on the right-hand side there. Okay, that's what we're talking about. Okay, so someone might ask, well, Bill, what if I come at a certain speed at that location? Okay, for example, you have, all these atoms, right? And they're connected to the Earth, right? And at that location, there's so many ropes connecting one atom to every atom on Earth. Now, would it be the same if you come at a great speed to that same location, you have the same number of ropes, but does that thing weigh the same? You see the problem? And here, let me illustrate it for you, what I'm saying here, the question. Okay, here you have an elephant. Okay, we're going to weigh the elephant. Better yet, we're going to weigh a single atom, hydrogen atom, of the elephant. Okay, so let me illustrate that so you see where I'm going with this train of thought. Here it is. Okay, we have a single atom, and at that location, right, that atom has so many ropes converging from every atom on Earth to that atom. Okay, so is that elephant going up or is that elephant coming down? That's one issue, right? And I'm saying at that location, that atom doesn't care. That atom has a single value. Okay, and that's the weight of that atom at that location. But what happens if the elephant is falling now? And I'm going to put them side by side just to show you, but it's the same elephant, the same location, okay? Except that one is falling, on the scale, and the other one is just sitting there. You're just weighing them, So the one on the left, you can look at it as a static scenario, and the other one as a dynamic one. Would they weigh the same? I mean, the number of ropes converging upon that atom that we just mentioned has to be the same, right? For example, here, let me illustrate that. Okay, that atom is the same. Again, keep in mind they're at the same location. I just put them side by side so you can see what I'm comparing here. In the right-hand side, we have the elephant falling, and the other one, the other just static. But at that location, that atom has only a certain number of ropes converging upon it from every atom on Earth. So do they weigh the same? One guy falling, the other one just sitting there, right? And the answer is very simple, really, to that question. Let me put this up here. You're comparing apples and oranges. In one case, you're comparing weight, okay? So even though you have at that location, all the ropes converging upon that atom, in one case, you're comparing weight against force because you got this guy is falling. You're comparing one frame in the Universal movie where the guy is falling. And obviously, you're not comparing now apples and apples. You're comparing apples and oranges. What you have is distance traveled. You have force equals mass times acceleration that you have to add on to that. because you're not talking, because if I only look at the number of ropes, that's a static scenario, there's no motion. But you're talking about motion that took you to that position. And so you have to add that motion to the number of ropes, okay? Because you're talking about something else. You're talking about the distance traveled now again. So again, you need to keep in mind what we're talking about here. One is distance separation, the other one is distance traveled. If you're going to talk about distance traveled, you cannot compare it against the distance of physics, which is just separation. So we have to keep in mind what we're talking about here at all points in time. You cannot include the distance traveled of mathematics with the distance of physics. Okay, if you're going to talk about weight, okay, then you're talking about separation, and for that you don't talk about what happened in the previous frames of the movie, okay, which is what you're doing if you include the travel of the elephant falling towards the scale. Okay,